Today we are going to discuss multiple regression analysis. Now that we all have already understood what a two-variable model is. In a two-variable model, we saw that we have one independent variable and one dependent variable. But in a multiple regression function, we'll see that we are going to have one dependent variable but more than one independent variable. So this is an example of a three-variable model. Here you can see that we have y, that is a dependent variable, and two independent variables, x2 and x3. So this is the case of a three-variable regression function. Now you can see that in this model we are having beta 1. Beta 1 here denotes the intercept term. It basically shows the average effect of all the variables that have been excluded from the model. Average effect of all those variables on y. So this is what it denotes. And if we assume the value of, or if we set the values of x2 and x3 to be 0, then in that case our y is going to be equal to beta 1. And as far as beta 2 and beta 3 is concerned, they are slope coefficients. In a multiple regression function, they are also known as partial regression coefficients. Now let's discuss the assumptions of this kind of a model. Most of the assumptions of a multiple regression function is same as a bivariate regression function, like it has to be linear in the parameters. And you can see that this function is linear in parameters. Second assumption is that there should be no covariance between the disturbance term and the variables, which means that there should be zero covariance between x2 and ui, as well as there has to be zero covariance between x3 and ui, which means that independent variables are independent of the disturbance term u. This second assumption becomes important because we know that the disturbance term, that is ui, is stochastic in nature, which means it is random, whereas x2 and x3 are not random in nature. They are going to have a fixed value. x2 will have a fixed value and x3 will have a fixed value as well. So there can be no relationship between disturbance term and independent variable, be it x2 or x3. Third assumption is that the mean value of u, or the disturbance term, is 0. Given the value of x2 and x3, the mean value of ui is going to be 0. We can simply state it as the conditional mean of ui is equal to 0. Fourth assumption is homoscedasticity, or constant variance of ui, which simply means that variance of ui is a fixed quantity, which is sigma square. Fifth assumption is no autocorrelation or serial correlation between the disturbances. So if there are two disturbance terms, ui and uj, then there has to be zero correlation between these two, or zero covariance. Sixth assumption is that n, that is number of observation or the sample size, has to be greater than k plus 1 whole square. And here k is number of independent variables. So the sample size should be greater than k plus 1 whole square. So if we want to run a model with two independent variables, in that case the observation should be, let's check, 2 plus 1 whole square. So 2 plus 1 is 3 and whole square of 3 is 9. Therefore, the observation has to be greater than 9. So this is one more assumption, that n has to be greater than k plus 1 whole square. Seventh assumption is that there must be variations in the values of x. It is very important, since if we assume the value of x, or if we set the value of x2, let's say, to be a fixed number, then it would be impossible for us to know the impact of change in the value of x on y. So there has to be variation in the value of x's. Only then we'll be able to see the impact of in its change on y. Eighth assumption is that there can be no exact linear relationship between x's, x2 and x3. There cannot be an exact linear relationship between these two. So no exact collinearity between the x variables or the independent variables. Our last assumption is no specification bias, which simply means that the model is correctly specified. Now this is read as expected value of y given the value of x2 and x3. Now let's talk about beta 1, beta 2 and beta 3. As we have already discussed that beta 1 is the intercept term, and beta 2 and beta 3, they are partial regression coefficients. Now what do we mean by that? Why they are called partial regression coefficients? Beta 2 measures the change in the mean value of y per unit change in x2, holding the value of x3 constant. We can interpret it as if x2 changes by 1 unit and we ignore the effect of x3 totally, we are keeping it constant, we are holding it constant, then in that case the mean value of y is going to change by beta 2. So it's going to change by beta 2 units. Similarly, when we interpret the value of beta 3, then we are going to hold the value of x2 constant. So the impact of x2 is going to be kept constant. So when we hold x2 constant, in that case, if there is 1 unit change in x3, then the mean value of y will change by beta 3 units. OLS estimators. We can see here that we are having two independent variables, x2 and x3. And the idea of OLS is to minimize the sum of squared residual. This is the same thing that we used to do even in the case of bivariate regression function. Now these are normal equations. To develop these normal equations, what we need to do is we need to differentiate this equation partially with respect to the unknowns, the three unknowns, that is beta 1 hat. So first of all, we are supposed to partially differentiate this whole thing with respect to beta 1 hat and setting the resulting expression to 0. And the same thing has to be done with beta 2 hat and beta 3 hat. And this is how we are going to get these three equations. So these are normal equations. Okay. Now let's see how can we know the values of beta 1 hat, that is the intercept. This is equal to y bar minus beta 2 hat times x2 bar minus beta 3 hat times x3 bar. So this is how we can calculate the value of beta 1. And here y bar simply means the mean of y and x2 bar is the mean of x2 and x3 bar is the mean value of x3 observations. For calculating beta 2 hat, we can apply this formula. Here what you can see is that y and x2, x3, all these terms are written in deviation form. So first of all, we'll have to find the deviations and only then we'll be able to apply this formula to find out the value of beta 2 hat. And for finding or calculating the value of beta 3 hat, we are supposed to use this formula. Once we have all the values of the deviations, we'll be able to find the values of beta 2 hat and beta 3 hat simply by applying these formulas. Now let's discuss the multiple coefficient of determination r square. For doing that, first let's have a look at this equation. So this is the simple equation of yi. So yi is equal to beta 1 hat plus beta 2 hat x2 plus beta 3 hat x3 plus ui hat. So this is the equation of y. Okay. And it can also be written as this, since the sum of these three terms is equal to yi hat. Okay. And if we want to switch this equation to its deviation form, this is how it's going to look like. So this is the deviation form of yi. That is why it is written in lowercase. Now after squaring both the sides and summing over the sample values, we have reached at this equation. This is simply the application of the formula of a plus b whole square. So you can see. So we are squaring this. A plus b whole square. That is how we have reached here. But since we know that there is no correlation between these two, there is no correlation between y and u. So that is why we are left with just two terms, the first two terms. Okay. Now after switching the value of ui hat square here, we reach at this equation. So we have just put the value of sigma ui square hat, and this is the equation that we get. And after rearranging this equation, we get ESS, that is explained sum of squares. And if we want to calculate the value of r square, what we are supposed to do is we are going to divide ESS, explained sum of squares, by total sum of squares, that is TSS. And after putting the values of both, this is what we get. Now let's compare r square and adjusted r square. The problem with r square is that when we add one independent variable which is inappropriate or which is irrelevant to the model, even then we are going to see that the value of r square increases. So if we take one variable which is completely irrelevant to our dependent variable, even adding such kind of a variable would increase the value of r square. This is why we adjust r square. And for doing that, what we do is we are going to divide the sum of square residual by n minus k. And we are going to divide TSS by n minus 1. So this is how we can calculate the adjusted value of r square. Now one interesting feature is that adjusted r square can be negative. The value of adjusted r square can be negative, and if it is negative, it turns out to be negative, then we are going to take its value as 0. But r square is always non-negative. So this is the major difference between these two. And one more important thing is that be it r square or adjusted r square, These are not enough to judge the adequacy of a regression model. There are other criteria which must be kept in mind while selecting a model. We'll be discussing those later on. Now, if we want to compare two models on the basis of the coefficient of determination, whether simple or adjusted, in both the cases, it is important that both the models have the same sample size and the dependent variable must be the same. So, if we are to compare these two models, can we compare these two models on the basis of coefficient of determination? No, we cannot. Why? Even if the sample size of both the models, let's say, is equal, still we won't be able to do it, since you can see that here the dependent variable yi is in its log form, whereas here it is not. So we won't be able to compare these two models using coefficient of determination, whether simple R square or adjusted R square. Neither of them can be used here to compare these two.